All right, today we're diving into something, well, pretty mind-bending. It's a new take on string theory, maybe the most ambitious idea in all of physics. And the big question is, what if, after all this time, we've been looking at it all wrong? So here's the big idea, the central question for today. What if our best shot at a theory of everything isn't really about little tiny strings buzzing around in extra dimensions? What if it's actually describing the geometry of probability itself? Yeah, I know. Let's unpack what that even means.
You know, for almost a century now, physicists have been on this quest, chasing this holy grail, the dream of finding one single beautiful theory that explains our entire universe. Everything, right? From the massive pull of gravity on a planet all the way down to the quantum weirdness that holds an atom together.
And for a long time, the frontrunner, the leading candidate for that job, has been string theory. And honestly, the core idea is just gorgeous. It says that if you could zoom in, like way in on any particle, an electron, a photon, you name it, you wouldn't see a little dot. You'd see a tiny, vibrating, one-dimensional loop of string. And how it vibrates, that's everything. It determines what that particle is.
But okay, for all its beauty, string theory comes with some serious baggage. I mean, some major problems. For one, it needs like 10 or 11 dimensions to work, and we only see 4. Where are the others? Then, its equations don't just predict our universe. They predict something like 10 to the power of 500 possible universes. That's the infamous landscape problem. And maybe the biggest issue of all? It doesn't make any predictions we can actually test. So for decades, it's been kind of stuck.
Okay, so to really get our heads around this new idea, we need to think of it like learning 2 different languages. 2 different mathematical languages that are both trying to describe reality. Let's start with the first one, which comes straight from string theory itself. We'll call it vibrating geometry.
So in this language, think of the universe as, I don't know, a cosmic guitar. You've got these fundamental strings, and they can vibrate in all sorts of different ways, right? They can play different notes. So if a string vibrates in one specific way, boom, we see an electron. If it wiggles in a different pattern, well, that's a photon, a particle of light. All the different particles, all the forces we see in the universe, they're just different songs being played on these tiny, tiny strings.
So here's the absolute key takeaway for this first language. You ready? The crucial point is that the geometry, the actual shape and pattern of the vibration, is what determines the physics we see. The geometry defines the reality. Got that? Geometry determines physics. Just lock that away for a sec. All right, language 1 is down. Now let's switch gears completely and look at our second language. This one doesn't come from cosmology or particle physics. It comes from the world of probability and statistics. And this entire language is basically summed up in one incredibly powerful formula called the master equation.
Okay, now you're going to see some math on screen, but don't panic. Seriously, don't worry about the symbols. We're not doing a math test. The only thing that matters is the core idea behind it. And that idea is actually pretty simple and really profound. This equation is just a rule for how probability works, how it spreads out across all the possible things a system could be doing.
Let's break that down. Imagine a ball rolling around in a big bowl. The most stable, optimal state is right at the bottom, right? This equation says the probability of finding the ball at any other spot in the bowl depends on its distance from that bottom point. The closer it is to the bottom, the more likely you are to find it there. The further away it is up the sides of the bowl, the less likely. It's really that simple. Proximity to the best state equals high probability.
And so, here it is, the punchline for language number 2. The most important point is, wait for it, geometry determines probability. Does that ring a bell? It should, because now we have these 2 totally separate languages, one from string theory, one from probability theory, and they're both telling us the exact same thing. Geometry is what runs the show. So what's going on here? What happens when you put these 2 languages next to each other? Well, this is where it gets really interesting. The argument is that they aren't just similar. They're not just rhyming. They are a direct one-to-one translation of each other. It's like we found a Rosetta Stone, but for fundamental physics. And this idea, this Rosetta Stone, might just crack one of the oldest and most nagging mysteries in string theory. You know the one I'm talking about. What on earth are those extra dimensions? We live in a 3D world plus time, so where are the other 6 or 7? We can't see them, can't measure them, so where are they?
And here is the radical answer this new perspective gives us. Get ready for this. The extra dimensions aren't physical places at all. You can't travel to them, they're not curled up super tiny. Instead, they represent the configuration space. Think of it like a giant geometric library of every possible way a string could ever vibrate. It's a space of possibilities, not a physical space.
And this idea just clicks into place so perfectly. Look at the core principle of each language. In string theory, there's this rule that strings always try to minimize something called action. It's basically the path of least resistance. Now, look at the master equation. What does it do? It describes how systems always gravitate towards the state with the minimum distance from the optimal one. It's the exact same idea. Minimize the action, minimize the distance. It's the same principle of finding the easiest, most probable state, just wearing a different costume.
And when you actually lay out the dictionary, the translation is just, wow, it's stunning. Look at how perfectly these concepts map onto each other. What string theory calls a string configuration, that's just a point in configuration space in probability. What string theory calls action, that's literally the square distance in the master equation. Even something as fundamental as a particle's mass turns out to be just its geometric distance from the ground state. It's not an analogy anymore. It's the same math. It's the same structure. Period.
So, okay, let's take a breath. If this is right, if this translation holds up, what does it all mean? Because the implications here are absolutely huge. This isn't just some neat mathematical trick. It could change how we view everything.
Well, for starters, it's a huge deal for string theory itself. It's almost like a get-out-of-jail-free card. It suggests the math, all that beautiful, complicated geometric structure, was probably right all along. We were just interpreting it wrong. The physical interpretation was the problem. Those extra dimensions, they're not hidden places, they're the shape of possibility itself. And that giant problematic landscape of 10 to the 500 universes, that's not a prediction of other physical worlds. It's just a measure of the sheer vastness of this abstract possibility space.
Okay, but what about testable predictions? See, one of the biggest predictions of standard string theory is this idea called supersymmetry. It says every particle we know and love should have a heavier twin, a superpartner. We've built massive machines like the Large Hadron Collider pretty much specifically to look for these things. We spent billions, and the number of superpartners we've found so far is a big fat zero. Nothing.
And this is where the new interpretation really changes the game. The old way of thinking says, build bigger colliders, keep smashing things together, and hope a new particle or a tiny extra dimension pops out. But this master equation view says, whoa, hold on, you might be looking in completely the wrong place. The evidence might not be some exotic new particle at all. The evidence might be something we can see all around us, checking to see if real physical systems, from the quantum to the cosmic, actually follow these exact geometric rules of probability. Maybe the proof has been hiding in plain sight this whole time.
So maybe, just maybe, string theory was never really a theory of things at all, not of little strings vibrating in space-time. Maybe it was always, from the very beginning, a theory about the shape of possibility. It's a beautiful and kind of staggering thought, that what we call reality, what feels so solid and real, is just the geometric landscape of what's probable. And we, you and I, and everything we can see and touch, we're just patterns of high probability, playing out in this infinite space of what could be. It leaves you with a final thought, doesn't it? That we are, quite literally, the universe's most likely story.